As we begin considering factorization, we're going to want to know when it's even possible to express elements as products of irreducible elements, which is where we're aiming towards. Now, in order to prove that that's possible in the cases that we care about, we want to understand a type of ring known as a Noetherian ring. Now, Noetherian rings are named for celebrated mathematician Emmy Noether, who worked in the early part of the 20th century and was a pioneer in understanding certain properties of rings that we're about to talk about, and showing that those properties were essential to understanding the structure and identifying which rings were most important to the overall theory. So one of the conditions that she looked at and is most famous for looking at is called the ascending chain condition. A commutative ring R is said to satisfy the ascending chain condition usually abbreviated ACC, if it satisfies the following condition. Every increasing chain of ideals eventually stabilizes. So that is to say that if we have a chain of ideals that looks like I1 is contained in I2, is contained in I3, going up like this is a chain of ideals, then there is some capital N such that for all n greater than or equal to, for all little n greater than or equal to big N, I little n is equal to I big N. So you can't have a chain of ideals that just keeps getting bigger and bigger and bigger and bigger in a ring which satisfies the ascending chain condition. Rings satisfying ACC are called Noetherian, after Emmy Noether. Now, there are definitely rings, there are plenty of rings which don't satisfy the ascending chain condition. That's why this condition is a useful one. But most of the rings that one encounters normally, most of the rings that one encounters when doing basic algebra are Noetherian, and Noetherian rings have lots of very good properties. Now, I should point out that the ascending chain condition is one that that makes sense to us if we start looking at ideals in familiar rings such as the integers. But the corresponding descending chain condition, saying that any descending chain of ideals stabilizes, certainly isn't something we should expect to happen very often. So, for the sake of example, let's let R be the set of integers z, and we will see in a moment in the next theorem that the integers are Noetherian. And so let's suppose that I start trying to write down a sequence of an increasing sequence of ideals. Now remember, all of the ideals of Z look like look like n times z, or the ideal generated by n for some n in z. So I can look at, for instance, the following chain of ideals. I can look at 20z, which contains all multiples of 20. That's contained in the set of all multiples of 10. So 20z is contained in 10z. And from 10z, I can reduce down. Maybe I could say that this is contained in 2z. And then if I want to go up from here, I don't have so many options. I can either stay at 2z forever, which means that I've stabilized as the ascending chain condition says that I should, or I'd have to go up to the whole ring itself, in which case I again have nowhere to go, and everywhere after that has to be the same. So this is just, of course, just one example of a chain of ideals. But if you think about what it means for one ideal in the integers to be contained in another ideal, this happens if and only if n divides m. So n has to be some factor of m. And so no matter what you start with, if I keep going to a factor of that, and to a factor of that, and to a factor of that, in particular, the numbers can only get smaller. And they can only go down so far. On the other hand, the descending chain condition can go on forever. So, for instance, if I try to construct a chain of ideals going the other direction, where my ideals get smaller and smaller and smaller, I can easily do so. So I can say that 2z contains the ideal 4z, contains the ideal 8z, contains the ideal 16z, which contains 32z, and on and on and on and on. And each time I move to the ideal generated by the next power of 2. And this chain doesn't stabilize. So rings which satisfy the descending chain condition are very, very rare in the grand scheme of things, whereas rings which satisfy the ascending chain condition are very commonly studied. Now, the ascending chain condition is the property that we want to use to define Noetherian. It's very natural, and it can be expressed easily, and it's usually, or often, the condition that we want to use. However, checking for Noetherianness is often difficult. And fortunately, we have an alternative characterization of Noetherian rings. Theorem 125. A commutative ring R is Noetherian if and only if every ideal of R is finitely generated. So if every ideal of R can be generated by a finite set, can be expressed as the smallest ideal containing a finite set of objects, that's equivalent to satisfying the ascending chain condition. So let's see how this proof goes. First of all, let's suppose that every ideal of R is finitely generated. We want to show that R is Noetherian, that is, it satisfies the ascending chain condition. To do that, we assume that we have some sort of increasing chain of ideals. So let I1 contained in I2, contained in I3, etc. be an increasing chain of ideals. And we're going to try to show that this has to eventually stabilize, that there's some point in the sequence after which all of the ideals are the same. Now, what we can do, we've got this infinite sequence of ideals. What we can do is we can take the union of all of them. We can take the union of all of the ideals in, and it turns out that this is an ideal, which is an exercise. In general, the union of ideals is not an ideal. However, when you're taking the union of an increasing chain of ideals, it turns out that that union will be an ideal, although it does take some work to do. But since it is an ideal, let's see. Oh, I want to give this the name I. So since I is an ideal, and we've assumed that every ideal of R is finitely generated, we have that I is equal to A1, A2, up through AT for some elements AI inside R. We don't know what they are. We don't really care. What we care about is that there's a finite number of them. There's only T of them for some finite number T. Now, notice that for each generator I, we have that AI is certainly contained in the ideal I because it's a generator of it, but the ideal I itself is this big union of a whole bunch of other ideals. So that means that we've got some element that's in a union of sets, which means that there exists some Ni such that AI is contained in I subscript Ni, in the nth ideal in the chain. And we can do this for each one of the each one of the generators of I. So now let's let capital N be the maximum of the Ni's for I going from little I going from 1 to T. We're going to claim that this is the moment when the ideal stabilizes. All right, so for each little I, we have that n little I is contained in I subscript capital N, since the little ni's are less than or equal to the capital N's, and we have an increasing chain of ideals. And so that means that AI, for each I, the generators AI belong to this I capital N. So this means that our ideal I, which is the ideal generated by this A1 through AT, is a subset of the ideal IN, because every one of the generators of the ideal I lies in the ideal IN, and I is the smallest ideal which contains all of these, so it's contained in IN. But IN itself is one of the ideals in this big union, which oh, sorry, I missed one step here. I want to say, so for any, let me say k greater than or equal to n, we have that IN is contained in IK, because k is greater than n, but IK itself is contained in the union of all of the INs, which is equal to I. So in particular, we have equality throughout, because we've got this chain of equalities of ideals, but we've got the same ideal on the left and on the right, and so all of these sets have to be exactly the same. So that means that IK has to equal IN. Since this holds for any k greater than or equal to n, it means that the chain of ideals stabilizes, and therefore the ring R is Noetherian. Okay, so that proves that if every ideal of R is finitely generated, then the ring R is Noetherian. For the other direction, we're going to say, now let's let R be an ideal, be a ring, sorry, containing an ideal I which is not finitely generated. We're going to prove that R is not Noetherian by demonstrating a chain of ideals which never stabilizes. Okay, so we're going to inductively define a sequence of elements, A1, A2, A3, etc., by the following. So let's just let A1 be any element of I. And for any n greater than or equal to 2, let's let an be contained in I, but minus the ideal generated by a1, a2, up through an minus 1. We know that this is possible. We always know that this is possible since I is not finitely generated, and so in particular it could never be equal to an ideal generated by a finite number of elements. So we can always pick something in I that isn't contained in the ideal generated by the first n minus 1 elements, which is finitely generated. So now consider the chain of ideals, the ideal generated by A1, which is contained in the ideal generated by A1 and A2, which is contained in the ideal generated by A1, A2, and A3, and so forth and so on. So in particular, if we note, we can note that any element AK belongs to the ideal generated by the first k elements, because it's one of the generators, but it's not in the ideal generated by the first k minus 1 elements because of the construction. We specifically chose it to not be contained in that. So that means that all the containments in the chain are strict. They're not just containments, they're strict containments. And so that means that R does not satisfy the ascending chain condition because this chain of ideals will never stabilize. So in particular, or by definition, that means that R is not Noetherian. Depending on what books you read, where you go to look this up, some authors will define Noetherianness of a ring based on the ascending chain condition, and some will define it in terms of all ideals of the ring being finitely generated. What Theorem 125 shows is that those two are completely equivalent, that we can define Noetherianness in terms of the ascending chain condition or in terms of there being a finite number of generators for every ideal being finitely generated, and they're exactly the same thing. So notice that trivially any principal ideal domain is Noetherian, because in any principal ideal domain, any ideal can be generated by a single element, and one is certainly finite, a finite number of elements. So any PID is Noetherian, but there are lots and lots of rings that are not PIDs, but are still Noetherian. One of the most important results that predated the notion of a Noetherian ring, predated our understanding of the ascending chain condition as being absolutely essential, is known as Hilbert's basis theorem. And it gives us a way of generating sort of Noetherian rings based on other Noetherian rings. That's given in Theorem 126. This is known as Hilbert's basis theorem. Is one of the greatest results from about the turn of the 20th century. And it says that if R is a Noetherian ring, then the ring R adjoin X, the polynomial ring in one variable over R, is Noetherian. Before we get to the proof, I want to point out that, in particular, this means that that the polynomial rings over the integers and the polynomial rings over any fields are all Noetherian. We know that the ring of integers is Noetherian because it's a principal ideal domain. And fields are also principal ideal domains. In fact, fields only have two ideals at all. One of them generated by the element 0, one of them generated by the element 1. So these two rings are Noetherian, whenever F is a field. This is one of the things that Hilbert's basis theorem gives us, which is so important. Okay, so we're going to prove the contrapositive in both of these cases. So we're going to suppose that one of these is not Noetherian and prove that the other is not Noetherian. So let's suppose that the polynomial ring R adjoin X is not Noetherian. And because we proved Theorem 125, we can take this to mean either that there's an ascending chain of ideals which doesn't stabilize, or we can take it to mean that there's an ideal which cannot be finitely generated. In this case, we're going to do the latter. Let's let I contained in the polynomial ring be an ideal which is not finitely generated. Now we're going to construct a chain of elements which we're going to use to build an ascending chain of ideals in the ring R, which we will show does not stabilize. So let's let F1 in I be an element of minimal degree and for n greater than or equal to 2, let's let Fn be an element of I, but minus the ideal generated by F1 through Fn minus 1 of minimal degree. Again, because I is not finitely generated, there's always going to be elements inside this set. I is never going to be equal to the ideal of F1 through Fn minus 1, and therefore we'll always be able to take something in it of minimal degree. And then, for all I, let's let AI be the leading coefficient of fi. Now, what we are going to claim is that we're going to be able to use these a's to build up an increasing chain which never stabilizes, just as we did in the last half of the previous proof. So what we're going to show is that each of these AIs does not belong to the ideal generated by the previous ones. So we'll do that by contradiction. So let's suppose that for some n, we have that an is contained in the ideal generated by a1 through an minus 1. We're supposing this, we're going to arrive at a contradiction. And this is as elements and the ideal, an ideal in the ring R, R itself. So that means, since this element is an element of the ideal, this means that an has to be equal to the sum of ri times ai's, I equals 1 to n minus 1, for some ri, for some elements ri inside the ring R. Now, by construction, we have that the degree of fi is less than or equal to the degree of fn for all I less than or equal to n. And this is because at every step of choosing the f's, we chose an element of minimal degree, which means that as we choose later and later f's, the degree of the f's that we choose can only go up. It could never go down, and so in particular, for any i's less than or equal to n minus 1, actually, I want here, although it wasn't wrong before. These degrees of the fi's have to be less than or equal to the degrees of the fn. So now, we can work in the polynomial ring over R of x, and let's let G be the sum I equals 1 to n minus 1, and we're going to be taking a combination of the fi's, and we're going to be doing a couple things to it. First of all, we're going to be using the elements ri that we had from the first, from what we just constructed, and we're also going to be making all of these fi's being multiplied by a power of x have the same degree. So we're going to take x raised to the degree of fn minus the degree of fi, and multiply that by fi. And we can construct this element inside R of x. Now, the leading term of G is obtained by looking at the leading terms of all of these polynomials. Now, each of these polynomials have degree fn, which means that if I want to find the leading term of G, I'm going to take the leading terms of all of these summands. So the leading term of G is the sum of Ri, Ai, which is the leading coefficient of these fi's, times x to the degree of f of n. And this is for I equals 1 to n minus 1. But we already know that the sum of the Ri's Ai's is exactly equal to an. So this is exactly equal to an times x to the degree fn. So that means that if I look at the difference fn minus g, the leading term of fn is an x to the degree fn, and the leading term of g is also an times x to the degree fn. And so in particular, this means that the degree of this difference has to be less than the degree of fn, because the leading terms are going to cancel each other out. Now, because of this, because the degree of fn minus fn minus g is less than the degree of fn, we can also notice that fn minus g has to belong to the ideal I. And this is because fn belongs to I and g belongs to I. We have that the element fn minus g belongs to I and it has degree less than fn. Since fn was the smallest, was an element of smallest degree outside of the ideal generated by f1 through fn minus 1, we have to have that fn minus g is contained in the ideal generated by f1 through fn minus 1. However, g is a combination of the fi's where I goes from 1 to n minus 1. So g actually belongs to the ideal generated by f1 through fn minus 1. And so that means that fn itself, which is equal to fn minus g plus g, has to belong to this ideal f1 through fn minus 1, a contradiction. All right, so we've arrived at a contradiction. If we go back to see what the hypothesis was that led to this contradiction, we see that it was the following. For some n, an belongs to a1 through an minus 1. That was the only assumption that we made, or the most recent assumption that we made, that led to a contradiction. Therefore, it must be false. So therefore, we must have that an does not belong to a1 through an minus 1 for all n. So that means that the chain of ideals a1 contained in a1, a2, contained in a1, a2, a3, and so forth and so on, it does not stabilize. Therefore, this tells us that R is not Noetherian. So, we've assumed that R adjoin X is not Noetherian. We've proved that R is not Noetherian. You'll notice that in the first case, we used the characterization of Noetherianness using infinite generation of an ideal. And in the second case, we use the characterization of not satisfying the ascending chain condition, having an ascending chain that never stabilizes. This is typical when working with Noetherian rings, where we'll switch back and forth between the two conditions very freely. So this finishes the proof. All right. So this allows us, as we mentioned before, to conclude that certain polynomial rings are Noetherian, such as the polynomial rings over a field or over the integers. We can build Noetherian rings using factor rings also. Theorem 127 shows us let R be a Noetherian ring and I an ideal of R. Then the ring R mod I is also Noetherian. All right, so for this one, we will use the finite generation of ideals to prove this. So this will also show the concept of pulling back an ideal along a ring homomorphism, which we've talked about some before, but we'll see another application of here. So let's suppose that R is Noetherian, I contained in R an ideal. Let's let pi from R to R mod I be the standard projection map. To be precise, pi of an element x is x plus I. All right, so we want to show that R mod I is Noetherian. We could do this, as I said, either by looking at the ascending chain condition or by looking at an ideal and showing that it has to be finitely generated. We're going to do the latter. So let's let J, which is a subset of R mod I, be an ideal of the ring R mod I. So, since pi is a ring homomorphism, pi inverse, or the inverse image, the pre-image of J under the map pi, is an ideal of R. Remember that the pre-image of an ideal is an ideal under any ring homomorphism. In particular, I want to call this ideal K. And so, since R is Noetherian, K is finitely generated. Let's say that K is generated by A1, A2, up through AT for some elements A1 through AT of the ring R. All right, we're going to claim that the images of these elements under the map pi are generators of the ideal J. We claim that J is equal to the image of is equal to the ideal generated by the images of these elements. So it's generated by A1 plus I, A2 plus I, up through AT plus I. Now, we want to show an equality of two sets. We need to show two containments. As is typical, one of these is immediate. So note that for all I, we have that AI belongs to K, and so that means that AI plus I, which is pi of AI, belongs to J. K is the pre-image of J, and so anything in K gets sent to J by the map pi. So this shows that A1 plus I, A2 plus I, up through AT plus I, this ideal is contained in J. So now we need to go the other way around. So let's let X in J be any element. Sorry, we want X plus I in J be any element. All the elements of the ring R mod I look like X plus I for some X in R. Now, notice that that means that pi of X belongs to J. So in particular, this means that X belongs to the preimage of J, which is K. Now, since K is generated by the elements A1 through AT, we can write X as a combination of Ri, Ai, I goes from 1 to T, for some Ri's in R. So now we want to show that this X plus I can be written as a combination of the Ai plus I's that we had before. So X plus I, our element of J, is by definition pi of X. Now X is equal to the sum from I equals 1 to T of Ri Ai, and pi is a ring homomorphism, which means that pi of a sum is equal to the sum of what we get when we apply pi to each of these things, but pi is also respectful of multiplication. So in a ring homomorphism, we can take the homomorphism applied outside a sum of a product and move it inside and apply it to each one of the factors in each of the sums. And in particular, this means that X plus I, the element we started with, can be written as the product, or as the sum of the products Ri plus I times Ai plus I. Now each of these Ri plus I's are some element of R mod I, and these Ai plus I's are precisely the things that we claimed were generators of J. In particular, this sum here belongs to the ideal Ai plus I, or A1 plus I, A2 plus I, up through AT plus I. And so, in particular, this tells us that any element of J has to be a subset of the ideal generated by these Ai plus I's. So that means that J is equal to A1 plus I, A2 plus I, up through AT plus I. So this proof, if we look at the proof and trace it through, does a little more for us than just tells us that the factor ring of a Noetherian ring is Noetherian. It tells us that we can find the generators of an ideal in a factor ring by finding the generators of the preimage of that ideal under the projection homomorphism, which is often a very useful thing that we want to do. So this means that almost any ring that we sit down and describe is Noetherian. Most of the time when we want to describe a ring, we're either describing it as a polynomial ring over a field or the integers, and the Hilbert basis theorem shows us that those are all Noetherian, or we're going to express it as a factor ring of one of those rings. So, for example, we can say that the rings Z mod NZ are all Noetherian, since they are factor rings of a Noetherian ring Z. We can also say things like, well, what if I take the real numbers and or polynomial ring over the real numbers, and I take the factor ring of that with the ideal generated by x cubed plus x squared plus x. Well, this is an ideal, and this is a Noetherian ring, therefore this is Noetherian. It doesn't matter what ideal you pick here. If you start with a Noetherian ring and take a factoring of it, you get a Noetherian ring. What we're going to see in the next lecture is that Noetherian rings are nice because in Noetherian rings, everything can always be written as a product of irreducible elements.